Hi, everyone. So we have recitation.
Hello.
Hi. Let me see. Okay, we can get started. So you wanna start, like, we can review review the chapter first, or we can just directly go to the question part. So today we can review chapter. Maybe we can look at some questions from chapter 11 and 12. So what do you guys think?
I'm fine with just going straight to some questions, unless anybody else wants to do something different.
Okay, we can start with some questions. So let's look at questions. So this is chapter 11. Okay, so yeah, so in this chapter, just like so this is kinetic energy, the torque, and the angular momentum, and the conservation of angular momentum. That's pretty much it. Okay, let's look at some questions from 52. We just check one question. If you have other questions, we can just do one by one. So you guys want to look at 52? So okay. Did you guys finish the reading?
I'm sorry, finish the what?
I mean, finish the question reading.
Oh, finish reading the question? Yeah.
So basically, here's a disk, and clock watch is here on the ring. And it's M. And then so there's an angular velocity of 0.26. Oh, by the way, last time we tried to convert the revolution per minute to reading per second, right? I forgot like what's the final answer we said, but okay. So R E M equal to, so one revolution is 2 pi, right? Just want to make sure we know how to convert per minute. Equals to 2 pi over 60 seconds. So it's 2 pi over 60 rad per second. per second. Okay. Okay. So I just wanna when I read this, just came to me. So we have the angular velocity, which is omega. And then walk halfway to the center of the disk. What is the angular velocity of this cockroach disk system? So so basically, we know this is a cockroach. It's on the rim, and then he started moving into halfway of the disk. And they were asking you, what is the angular velocity of the cork disk system? So like when we think of it, when we saw this question, what's the first thinking do you know what the question, what the kind of knowledge they want you know? Like what's the knowledge? What's the point that they were asking you this question? What they want you to understand?
Conservation of angular momentum.
Yeah, that's correct. Anything else? So yeah, that is the most important one. You have to understand conservation. So basically, the system is consists of a disk and a cockroach, right? And we have to know the conservation. Where's my note? But anyways, we have to make sure. So if we know like what they are asking for, we just try to get all the information and then make them together and then put it into the equations, right? Let me see. Okay, so how I can share another screen. So what I'm gonna write. The text. Okay, I can write here.
So, as far as I understand it, what we're looking for is what the angular momentum is of this system. And we know that angular momentum is the rotational inertia times the angular velocity.
Mm-hmm.
And we know what the angular velocity is, and we can probably figure out what the initial uh, rotational inertia is, but we need to figure that out. And then once we figure out what that initial rotational inertia is, then we know that that momentum that we've created is going to equal this new thing that is going to have a different rotational inertia. And so then with that that L that we get, that is the first inertia times angular velocity divided by the new rotational inertia is going to give us our new angular velocity.
Yes. So can you tell me what is changing between these two states?
The angular the rotational inertia is changing, but how to calculate that accurately so that I know exactly I don't exactly know how to calculate that. I know that it's the sum of the masses times the radius squared, but then you also have so the mass so the one mass, which is the cockroach on top, is moving, so that's going to change the inertia, but I don't know how to do the disk itself.
So okay, so let's try to so before the cockroach is on the rim, and after it's in the middle of the well, halfway to the center of the disk. So we have to understand what is changing. So for the disk, it doesn't change anything because if it's rotating, it's still the same. Even
So
okay.
I think what would change would be the Because I know for a particle, which I'm assuming that the cockroach would be a particle, it would be mr squared. And then if I'm not mistaken, I think for a disk, it's 1/2 mr squared. So I think in the beginning, they're going to have the same um, omega in the beginning. And then the two, it would be mr squared for the cockroach plus 1/2 mr squared for the disk.
But we can actually get rid of that disk because we don't care what the 1/2 mr squared is of the disk because it's going to be on both sides, as you just said. The disk doesn't change. So all that we care about is the cockroach itself, what its previous inertia is and what its current inertia is.
Yeah, and then the only thing that would change would be the r, right? It'd
Yeah.
be the r would be the dependent thing there because it crawls halfway to the center.
But we don't know what its what the radius is of this disk.
That's a good point. I guess it would just be r, and then is there does this one have solution? I always forget. Is it even? It's it's even that don't have.
Evens don't have solutions. No.
We just here we try to make sure we understand we are understanding the right way. So when we see a question, how we analyze them. So we have to know so the difference between if you are comparing two states, you comparing okay, the first one is the disk and the cockroach, and then the cockroach is moving, which means that the radius is decreasing, right? And we want to make sure we have the same angular momentum from the both states. So we just try to.
I just realized it doesn't matter what the radius is, because if he's going halfway in, then because it's the radius squared, it's 1/4 of that. So this new thing is going to be 4 times what the original one was. So the new angular velocity is going to be 1/4 in order to be able 1/4 of that original omega in order to conserve angular momentum. Correct?
So here, okay, we have to understand the angular. They are asking you angular velocity, right? This is like when we angular velocity is the how many angles it passes every second or every minute, right? So if
yes.
they are asking you what changes before when the cockroach is here, it's 0.26 rad per second, and it moves here, and then so for the entire disk. So the only thing that didn't change is the angular velocity. You know what I mean?
No, the angular velocity
It's the omega, right?
Is the omega, but the angular velocity is going to change. Otherwise, it wouldn't ask what the new angular velocity is. The angular velocity has to change because the rotational inertia is changing. And the only difference between the two rotational inertias is that distance of that cockroach as it makes that half of a radius movement inward. So whatever that radius squared was, this new radius squared is going to be 1/2 of that radius squared. 1/2 of that radius, which makes it 1/4.
Okay, let's try to write them down. So we wanna write down the cockroach's initial, right? It's small r, mr square. This is cockroach's initial. And why we want to do initial is because we want to get the angular momentum, right? L equal to so I times omega. So this is for the cockroach, and for the disk.
The disk doesn't change the purposes of this equation, so it doesn't really matter.
Yeah, so the disk doesn't change anything, so we can. Okay, we just analyze the cockroach, and then after the cockroach moved to the halfway to the center, then the r changed to 1/2, right?
Yes.
And we have to, okay, how we make it, okay, use a different color then. Okay, so then the new one will be, I2 equal to M times 1/4 R squared, right?
Right. So that means, actually, I was wrong. It means the omega needs to be 4 times as big because of the addition of that 1/4.
Yeah.
So it's whatever that angular velocity is, we just multiply it times 4, and then that gives us our new angular velocity.
Yeah. So times omega. This omega is a new one. So this new omega is what we're looking for. We want to, okay, let's put on a question mark. What is this one? What, this is L. This is L. And because this is system, the angular momentum remains the same. I mean, like it's conservative, right? A equal to this one, equal to I, which this I is mr square. So we just change this one to this one and the times it, just put everything together to make the equation. So it's mr square r square times omega. So that's why you can calculate what is omega 2, right? So the only difference is the r is different, and the what remains the same is the angular momentum remains the same, right? Winsor, is that what you're saying?
I'm sorry, can you repeat that?
Oh, sorry, who is talking? I saw it was you. Sorry. I don't know.
Windsor was doing some talking, but it was mostly me,
Oh,
Alex.
sorry. What's your name? You are Alex?
Yeah.
Oh, okay, Alex.
So yes, that was what I was saying, was that the new I2 is the same thing as I1, except that you've got an extra 1/4. And so to accommodate that, W2 or omega 2 just needs to be 4 times as big to make up for the 1/4 that's being included for I2.
Yeah. Okay, so so after, yeah, so anyone has a question for the first part?
So yeah, I just because I wanted to double check it. You know, they I know it's not perfect, but when you Google, like, you know, copy and paste some stuff, the answers sometimes come up with like Slater or whatever. And I don't think we were like, I mean, based on what they give, we were, you know, we're really close to doing the right thing, but we can't just get rid of the inertia of the disk, because the first you know, if you factor out the initial angular velocity on the initial side of the angular momentum, you know, you end up with the plus sign in between, and it's, you know, it's, and then if you factor out the final angular velocity on the final side, it's not this, you know what I'm saying, like it's not the same. You can't just cancel that because there's a plus sign. You know, it's not just factors that would cancel, and you can't cancel it all because the r on the final side, it would be basically the way they have it worked. That would be m1 omega naught r squared plus 1/2 m2 omega naught r squared for the initial side, and then for the second side it would be m1 omega final r over 2 squared plus 1/2 m2.
Oh, yeah, I know what you mean.
I'm
Oh,
sorry.
actually, yeah. So because the omega is changing, so
Yeah.
it also applies to the disk.
Well, yeah. I mean, yeah. Obviously the omega is changing, and when you
Yeah.
factor it out, it's you can't. It's not like you can't just cancel the inertias of the disk on both sides because that plus sign in between.
Yeah, I see
Oh,
what you mean.
I'm sorry. Getting lost on where the plus sign is that is
Um,
getting in the way.
so if you So like if you literally write it out, like if you write m1 omega naught r squared plus 1/2 m2 omega naught r squared, and that's the initial angular momentum, and then equals, and then it's going to be the final on the right hand side, m1 omega final r over 2 squared plus 1/2 m2 omega final r squared. And so because when you factor out that, if you factor out the omega final on the right hand side and the omega naught on the left hand side, I understood, like I saw what you're saying. You're like, oh, the inertias should be able to cancel, but because of the plus sign in between, you can't. You know
So,
what I mean?
let me see if I understand this, because I tried to write it down. What you said, you spoke a little bit fast for me to write, but yeah, no. So what you have is you have your m1 omega naught r squared plus 1/2 m2 r squared, right? Or is it 1/2 m2 r squared omega naught?
Yes, there's the
There's
omega
an omega naught for both of them.
Yes.
And then that's why, okay.
Yeah,
So
if you factor it out, and then if you were to try to cancel, because obviously you can't.
so we're not combining the cockroach with as part of the system when we're doing it.
As far as this situation went, I mean, well, it wouldn't be.
Oh wait, I guess you would get that same thing even if it were part of the system, because you'd be doing that plus that times omega naught. Okay, I see. Yeah, so exactly. If you factored out the omega naught, it would just be
m1 omega. I mean m1
r squared
plus 1/2
m2 r squared.
But then on the other side, it's not the same exact. If you factor out the omega final on the other side, you get
right
1 r over 2 squared plus 1/2 m2 r squared, and so you
can't. m1 r.
But then from there, so if you factor out the omega final on the right hand side, you can literally just divide the first side by the right hand side, and you know what I mean. You get the whole initial side divided by m1 r over 2 squared, which, like you said, would be r squared over 4 plus 1/2 m2 r squared equals omega final. And then you can factor out the omega naught out of the top half of that, and that's as far as I got as far as writing it down.
Yeah, well, I mean, because the thing is, though, that so I did the factoring out omega naught. So we have omega naught on the top of the fraction is going to be omega naught times the quantity m1 times r squared plus 1/2 m2 times r squared, and that's all over m1 r squared over 4 plus 1/2 m2 r squared.
Yeah.
And all of that is equal to the omega final.
Yes, exactly. That's exactly what I have. Yeah.
Okay, so but we don't know we know what the mass is of the cockroach, but we don't know what the mass is of.
It says mass is 4m for the disc, so you could replace m2.
Oh, wait, the disc is given. Oh, the disc is given, but the cockroach is a cockroach is just given as m.
Yeah, it's m and then 4m, so you could substitute for m1, 4m for m2.
So then we get 2m for the two spots, and then for the two because if it's 4m, then it's 4 divided by 2 gives us 2m. So then we have omega naught times the quantity 3m r squared all over let's see here, 9/4 mr squared. Yeah,
and then because the end result that you get is that you get when you simplify it all, you get 1.33 times
what
omega.
You get so you get 12/9, which would be 1.33.
Exactly. Yep. And you get that times omega naught, and omega naught is given, and so then you get to the final.
Right. So, okay, that makes sense, because then you can actually, once you have those things together, then you can cancel out the mr squared, and then you just have 4 times 3 over 9 times omega squared, omega naught, and that gives us our omega final. Okay. Mm-hmm. Yeah, I'm still struggling so hard with this rotational inertia, because it's really not clear to me, like sometimes how to figure it out.
Yeah, that's, I mean, he said it's going to be, we won't have to calculate it, which is good.
Right.
Because I
But like
noticed,
half of these problems like that
yeah,
is part of the I don't see how he wouldn't. Like, I
no,
mean,
I
I
know
know
what you
he's
mean. Because there's, yeah, I would assume that he's just going to be like the rotational inertia for this, just like the same thing with like the revolutions per second and the radians per second. I highly
right.
doubt he's going to give us that, where we'd have to, because he never, he
Oh
never.
yeah, we don't ever have to
I think it's
change
just going to be
units.
omega equals, and then it's going to be a numerical quantity. You know what I mean? And then it's
Right.
just, yeah. So there's certain things that, and you're right though, because like half these problems that I've done, that is half the work of the problem is converting.
Exactly.
Yeah, and it's a pain because
Yeah.
I'm wasting my time with this.
Well, I mean, that's the thing is like I mean, like if half of these problems really are just about like us not needing to go through figuring out rotational inertia, like I have spent literally hours trying to understand how to figure out rotational inertia so I can do these problems. And it, like if he's not going to give us it, then I don't know what he can ask of us in these sections. Like there's just so little information that doesn't involve needing to figure out rotational and understand rotational inertia. Like,
Yeah, I have a feeling we're going to get a lot. I think we're going to get a lot of what's called equilibrium problems, because
yeah,
those seem to be the most like problem solving ish ones. Because a lot of these ones, just like you're saying, like if you're given the rotational inertia, like there's, it's almost all of these were like conservation problems. Like it seemed like almost it was the solution like almost every time,
right.
was some sort of conservation. But the equilibrium ones I noticed were a lot more problem solving and that
Right.
seems more up his alley so far.
Yeah, no, I think that you're not wrong. And like, which that reminds me, and Judy,
Yeah.
I don't want you to feel bored while Windsor and I are talking
It's
here,
fine. I think that's good. That's good.
but
Really,
I have a question for you regarding equilibrium, which
it's
is, yeah, which is chapter 12. But so since we're talking about equilibrium stuff, I figured that I would ask really quickly here. When dealing with a situation of a of some kind of stick being like a teeter-totter kind of thing, and you're trying to figure out where that mass is actually pushing down its weight, pushing down its force. Like, we're not talking about any extra added weights to it. We're just talking about it itself. They're at the ends, correct? So like if you have a teeter-totter that's balanced in equilibrium, what you have is half of the teeter-totter's weight is pushing down on one end of the teeter-totter, and half of it's pushing down on the other, correct?
teeter tot is what?
A T cross where you have just something holding up a bar in the middle.
A torque?
No. I'm not talking about torque. There would be torque to it, but I'm saying that if you just have a T cross, you just draw a T right now, just big T.
Oh, okay.
Just
okay.
So on the left end of that top of that T, that there's a force pushing down from the weight of that T, and then on the right end there's another force pushing down, and those are going to both be just like half of the weight of that bar, right?
Yes, you mean the R?
Yeah,
Wait,
the bar with that cross bar that you put at the top of the T, whatever we want to call it, that
Okay.
that whole length, that whole horizontal length
Okay.
has a weight to it,
Okay.
right?
Yes, it has a weight.
And so half of that weight is pushing at the very far end, correct? Of the far left end of the T.
So you mean these two are their weight?
Right. Well, those two are half of its weight, right? Each of them are half of the weight for the whole thing to be.
I mean, this force are external or just itself?
Itself.
Itself, I don't think. I mean, if it's just like remain stable, not like rotating or something.
Right.
You have to find the center of gravity. So if this is a rod, and the center of a mass is here, which is here.
Right. So the center of mass then means that's where all the weight is pushing down.
Yes. So that's all the weight is pushing down.
Pushing down at that point, it's not okay, because I was working on another equilibrium problem, and it was asking how to figure out the actual mass of that bar, that cross, and I was struggling with it because I wasn't sure how to appropriately assess where the oh, I understand now. Okay, I'm good. I figured out my own question. Thank you.
So you have an exam from chapter 10 to 12?
Yes.
It's the third midterm.
I'm sorry, say that again?
I mean the third midterm.
Yes, it is the third exam. No, this is the fourth exam. This is the fourth.
Okay.
No. This is the fourth exam. We've done 3 exams so far, so this is the fourth.
Oh, do you have any other questions? We can.
I say we go back to doing more problems, but maybe, and Windsor, you can throw in some thoughts, or someone else if they want to.
Yeah.
Maybe we should just jump to doing chapter 12 things then, if you think that's where we should spend our time.
Yeah, I mean, it's unless anybody else, because I know, with the with 11 tac 1 through 11 tac 6, it all seems like it's working up to the angular conservation of momentum, angular momentum. You know what I mean? Like, it's the same thing with like the 10-1 through 10-3 are kind of all working up to 10-4 through 7. You know what I mean? Like, they're kind of being the fun. Like, I don't think we're going to get any questions that are framed in that way. I think we're going to get more like conservation of angular momentum and what's it called? Equilibrium ones. I could be totally wrong, but it doesn't, you know what I mean? Like, the way when I went through the textbook and I looked at those problems, I'm like, these are the fundamentals, and he never asks about the fundamentals.
He never asked about the fundamentals, and he never asked us to do cross products or anything dealing in two-dimensional or three-dimensional space. So I figure like that's all off the table. But I think that you're not wrong that it should be conservation of angular momentum and then equilibrium seem like the most likely places that he's gonna.
Because even with the stuff in all of chapter 10, you know what I mean? Like the torque and the kinetic energy, like, I don't think we're gonna get one that's just, I could see that being incorporated as it is, you know what I mean, into an equilibrium or a conservation of angular momentum problem. Cause like, I don't think he's gonna be like, oh, find the torque given these values, he's gonna use the torque in an equilibrium problem type thing. That's
so. I think that you're right, but I also think that he's going to ask for questions like, for example, if you have a mass, and he'll say what the inertia of the mass is rolling down a surface.
Oh, yeah, you're right.
Rolling an angular surface, and I'm I'm concerned that he'll also throw in like some part of that rolling is sliding, and then at some point it stops sliding. Like there was a problem that I did that was with a bowling ball.
Because it's when it's sliding is meaning that the friction's doing some work or something like that. That's like
it means that the friction hasn't gotten up enough to actually stop it from sliding along yet. So the friction isn't up yet, and then the friction, as it starts to spin the ball a little bit more and more and more, it gets to a point where it actually is enough, and then the ball just stops sliding and just is exclusively spinning. And that's the part where I'm really not good.
Yeah, no, that would be a really tough problem. if I saw that, I'd probably be like, I'm better spending my time on the next one.
Fair. But the example, Judy, if you go to, I'm trying to remember, it's in chapter 11 that I did a bowling ball problem. Let's see here.
I think you're definitely right that there's going to be a rolling problem because like he loves using the inclined plane and the and you're probably right. There's probably going to be one of those.
Yeah. So I was trying to figure out where that bowling ball problem was, because that one is what really gave me my let's see here.
Oh, you mean this one?
Oh no, it was. I know exactly where it was. Hold on a second. My brain is. I'm seeing some of these things, and I'm starting to remember when. Solid ball, hollow sphere, constant horizontal. We're in the right area here. Brass ball. Right. There we go. Measure. Oh, number 15. Number 15 was the one that I did.
So yeah, we can just say work on this together.
Yeah, it's this kind of like I worked through it already once, but I'd like to work through it again just because like that's really incorporating the it might be sliding down a surface and also the mixture of there's a portion of this that it is sliding and there's a portion of it that it's rolling and you need to figure out like when it's sliding and when it's rolling, and that's really tough for me.
So yeah, okay, let's work on this together. R is 11 centimeter along the length, and the ball sliding on the length with initial speed. This is linear speed, 8.5. Initial angular 0. So it's not rotating. The coefficient kinetic friction, ball and length 0.2, kinetic friction force Ft acting on the ball cause linear acceleration of the ball when producing torque that causes the angular acceleration of the ball. When speed v has decreased enough and angular speed has increased enough, the ball stops sliding and then rolling smoothly. Stop sliding, stop, and then rolls smoothly. So basically the ball is gonna roll and stop sliding. What is the V in terms of omega? During the sliding, what are the balls? Linear, okay. So this is, the balls at first has a linear velocity.
Yes.
It's sliding, it has the frictions. So after a certain time, then the friction causes the ball rotating, which is like so the omega will increase. Well, because the friction, the linear speed is gonna decrease. So in the end, the ball is gonna rolling. It's gonna rolling, but it stops sliding. So sliding means like I guess. Sliding is like you use the same surface to slide, right? To move. And if you're
sliding is that there's no angular velocity because all that's happening is that it's moving without rotate. It's moving without rolling along a distance.
So you only this point, only on this point contact the surface.
Yes.
Right? Yeah. Okay. So we want to know when the ball stops sliding and then rolling smoothly, what is the linear velocity in terms of omega? Because we know V equal to R omega. So I guess we have to represent, we use omega to represent V, or we get a specific number.
We'll use it, ultimately get a specific number for omega.
Okay. So let's see. So we have, do we know the mass of the ball?
No, we don't, but I don't think we need it because we're talking about kinetic energy, which is going to be the 1/2 mv squared plus 1/2 I omega squared. And so the m is going to just disappear because we're also getting some relationship stuff. I think so.
So we're gonna, so this is also angular momentum, right? Wait.
No, I think this is in the kinetic energy of rolling part.
Yeah, this is just the kinetic energy of rolling. So there is no Angular momentum. I mean, maybe we could use angular momentum, but that's not what the problem's wanting us to do.
Yeah, I think we definitely need mass to do the angular momentum.
Yeah, kinetic. Kinetic energy. So we have. So what do you think we should write? It's like half of the initial omega square plus half mv square. Wait, what is changing? The variable here is the friction, right? The friction cause the linear speed decrease
and causes the angular speed to increase.
Okay, let me think how we combine them. So we have to, anything constant here? Okay, so we start to write down then the friction. So the friction, let me see. Equal to mu mg, and this causes the friction. Wait, what equation you use for let me see, for the kinetic energy? It's 1/2
mv squared plus 1/2 I omega squared.
I omega squared, yeah.
And in this case, because it is a solid sphere, that I is, I have to look it up in the book because I don't know it off the top of my head. Hold on a second.
Oh, the I equal to
2/5 mr squared.
And this is I omega squared.
So I think just for part A though, because it does say when the ball, when speed, blah, 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 the ball stops sliding and then rolls smoothly. What is V in terms of omega? And that's just it's just V equals omega times the radius. And I think that's it for part A. I'm sure.
No. But the thing is though that the linear velocity will actually decrease as the friction works.
No, I completely agree. I think it's just in that one portion because it says, when speed is decreased enough, angular speed is increased enough, the ball stops sliding and then rolls smoothly. And
Yes.
For this, it says for a wheel of radius r rolling smoothly, the velocity of the center of mass is just omega r. So I think it would just be in terms of omega, because that's what it's saying. It says, what is the V in terms of omega? I think it would just be V equals what is the 11 centimeters? So 0.11 meters times omega would be the new V in terms of omega. I think that's, obviously.
Oh, yeah. Yeah, I mean,
just for part A.
Whatever that, yes. That is how we would figure out part A, but we have to figure out the point at which the omega is actually going to stop the ball from sliding, so we know what that point is. That's really the big question here. And I know that there was some element of incorporating friction, and there was something mentioning this in and I know can go to the part of chapter 11 that talked about it, because I read it like 6 times and I still didn't understand it. But
wait, what this part? Did I miss something?
Hold on, I'm gonna say it in a second once I find it here. So there were, so you have the rolling smoothly, forces of rolling, but there was something that I thought that I read here that was talking about there's a point at which that you have to recognize that or maybe I actually read it when I was just getting assistance with this problem online that I saw it, but there is something that has to be set to the velocity, or omega r has to equal the velocity at some point, so that uh, I'm dropping the ball here. I don't really remember. That's part of the issue, is that I'm so lost here on like how we figure out the point at which it stops sliding when there's been enough angular, because there's an angular acceleration happening because of the force of friction. I know that.
Yeah, no, it's because that the how far does the ball slide and how long are parts D and E. So I've noticed with these problems in the textbook, you kind of have to do, you know what I mean, like A and B, and before, because you're right, like we definitely probably need the angular acceleration, and that we'll figure that out in part C. You know what I mean? Like I feel like doing these piece by piece in this can.
Well, sure, but the issue is though that without knowing the point at which it has stopped sliding and started rolling, I don't know how we're supposed to know what the linear velocity is at that point.
Yeah, no, I understand what you're saying. My only suggestion, I mean, maybe it would become more apparent to us if we, you know what I mean, if we just do A, B, and C first, and then it'll be like, oh, you know what I mean? Like if we're, because it made us write the velocity of center mass in terms of omega. I like just knowing how these types of problems work. It's probably going to end up, it's probably going to end up, what's it called, being at some point.
But what I'm saying is though that like what I think that you're suggesting for, and I'm going to check this just to make sure that I'm not crazy here. 8.5 times 0.11 is so the for done it looking at measure this is number 13 of chapter 11, right? So no, this is, what number is this?
15.
It's 15. Yeah, 15. Yeah. So the number that it has for that omega is, oh, it just has it as negative in terms of, oh, I understand now.
Yeah, that's what I'm saying.
Okay, now it makes so much more sense what you were saying, and I'm sorry, I just did not understand the question.
Nah, you're good, man. This stuff's not easy.
So okay, so it's just
it's
negative
negative
0.11 times omega, whatever omega is, and we don't know that, but okay, I'm good.
So that means what negative?
So what that means is that for part A, all it's asking for is to use the equation of what does it mean to have this thing have the linear velocity in terms of angular velocity, and that's just multiplying the radius times the angular velocity. Multiplying the radius times whatever that new angular velocity is going to give us our linear velocity, and they didn't really care what the angular. They didn't want us to figure out what the angular velocity was at that point. It was just a general, using the letter omega, or at least that's what the back of the book had, was just like that part is just, it's omega times negative.
You see my experience, it's like a so when it's pure rotation, so the way is like a they're opposite, and then the pure translation is just like heading to the same direction. But when you are rolling, you are in a rolling motion, so that means the weight cancel a lot, right?
Yes.
Well, because it's just in terms of omega, like you said, the reason it's negative 0.11 omega, I'm assuming is because if we choose positive x as the positive for velocity for v, then omega, when you think about a ball rolling forward, omega is going to be negative because it's moving in the clockwise direction. You know what I'm saying?
Yes. Omega is moving in the opposite direction from the velocity.
Yeah, exactly. So this is just showing v in its relation to the center of mass. This isn't showing v in its relation to omega. It's easy, just like, if right is positive and the ball's moving right, so we choose v as positive, then think of omega as the what's it called, the rotational thing. You think about it, it's a ball rotating, like a bowling ball rotating forward, it's going clockwise. So that's why it's negative 0.11 omega, because omega is negative if V is positive.
Wait, if so omega y and omega is negative?
Because typically, I'm assuming this. He said it said negative 0.11 omega as the answer in the book, and I'm assuming because
Yes.
Clockwise is typically in these problems associated with when you're dealing with angular velocity. Is clockwise is typically negative. Counterclockwise is positive. So if V is positive, then omega is negative, and vice versa. If you can choose clockwise to be positive, but then V is going to be negative, if that makes sense.
Yes. So you're always going to have a negative, whichever way you do it, is going to be some negative associated with it.
Yeah, because if you're choosing counterclockwise as negative, that would mean that you're choosing, you know what I mean? That would mean you're choosing to the left as the positive direction, and that would make V negative.
Right.
Okay, let's say for example this one. The
Okay, go ahead.
V is how could, I mean, for omega we can say it's let's say we can define counterclockwise is positive and clockwise is negative, right? Or like we can define ourselves. We can define
Yes.
either, right?
Yes, exactly. You just have to be consistent with it.
Okay, let's say we define omega as a positive here. It's counter, it's clockwise. And then why V is negative then?
Because when
Because I mean, I guess it would be like this picture makes it look weird because it makes it look like omega is moving towards the right. But if you really like think about that wheel's motion, it's like pick a point on the wheel, right? Like pick a point right there on the edge of the wheel. Is that point moving left or right? That point's moving to the left, right? Like you understand what I'm saying? And so if you're choosing that point as moving to the left as a positive thing, that would mean that V going to the right is now negative. And in this situation, we chose V going to the right as positive. So that would mean that point going to the left in a clockwise direction is negative.
Yeah, this is a little bit brain busting, but I am absolutely agreeing with Windsor on this one.
Yeah, I think that's why they wrote that little P right there.
Yeah. So like let's say the wheel is moving, so the P is going left side.
Yeah.
Exactly.
But the velocity is going the other direction. So.
And if you're choosing left as positive, then V is negative. But in this way, they chose left as negative and right as positive. So omega is negative.
Oh, I see. Then the V will going left side.
Yes.
Okay, so it's opposite direction, right?
It's just the way that I made sense of it in my brain. But yeah, like if you just took that image and imagine it doing like 1/4 rotation, right? And that P moved to the left right there, and V is still going to the right. So they're in opposite directions.
Yeah.
You know, I'm sure that there's a better way to explain it, but so you have to choose, they're one's negative, one's positive. And you can just choose which one, but once you choose, you have to stay consistent with it.
Oh, interesting. So, okay, let's see the sliding ball.
So we know now what the V is in terms of omega. So now during the sliding, the ball's linear acceleration and angular acceleration. So finding the ball's linear acceleration means that what we're doing is we're actually calculating there's a linear deceleration happening because of the force of friction.
Yeah.
And so the force of friction is the only thing pushing against it. So it is so the only force is happening in a negative direction, and that is mu n is equal to, and then what we want to find is, but then that would mean we would need to know the mass.
I mean, you see, so the friction is mu n equal to mg, right?
Right.
And it's mu mg is the friction, and you need to know the acceleration, which is the a. So it's canceled out by the m is canceled on both sides.
Oh, because mass times acceleration, right?
Yeah.
So it's just mu g
Yeah.
is equal to the linear acceleration. Got it. And so since mu g is our linear acceleration, then our angular acceleration
Oh, you
and
just
this
divide
is
by r, right?
is just our linear divided by r. So it's mu g over r is our angular acceleration.
Sounds
And
good.
the angular acceleration is increasing. Unlike the
Oh, you have to check the positive or negative.
yeah, because the angular acceleration, it's speeding up as the linear slows down, because the friction is causing the ball to not move quite as fast in a linear way, but because of that, the ball is starting to rotate faster and faster. So the angular acceleration is increasing and the linear acceleration is decreasing.
Yeah, the angular is, acceleration is positive. Linear is acceleration is negative because it's decreasing, and the angular is increasing.
Okay.
Yeah, I think it's, I mean, for a decreasing, I think it's easy to think about it as like the like in terms of forces, you know, friction's pointing to the left, so friction's negative. So negative mu mg equals ma, negative mg equals a. There you go.
Yeah.
So mg, I mean, yeah, mu. I'm sorry, not mg. Mu g would be equal to negative a.
Right.
Type thing, yeah.
So then the next thing is, now that we know the linear acceleration, angular acceleration, how long does the ball slide? So that's the real question. We now have the acceleration, but the question is, oh, that's why. So we need to find the point at which v is equal to r omega. So the omega at the very beginning is not equal to r omega is not equal to the initial velocity, linear velocity. So as those accelerations change, we need to find out the point at which, boom, they actually meet. When they meet at that point, then the ball starts rolling smoothly, and then it continues like that.
Yeah.
Oh.
So omega 0, omega, the initial omega is 0, and we want to find the final omega, which is v divided by r. This is the omega final. So we want to find it, and we know the acceleration.
So basically what we have here is our, for our velocity equation, a, which we figured out the negative a of linear velocity, plus 8.5, which is the initial velocity, is equal to the radius times omega, which is the linear acceleration, or the angular acceleration, times t. And there's no initial angular acceleration, so that tells us that. And then what we want to solve for with this is, we want to solve for, what do we want? What do we want to know? Why do we care about any of this? Oh, sorry. We're solving for t. And so then we put 8.5 is equal to r is equal to t times the quantity r omega r alpha plus a. And so that means it's 8.5 over r alpha plus a is equal to the amount of time that it takes for the ball to stop sliding and actually hit a point where it's rolling smoothly.
So can I ask, what's the answer for question A? What's the
negative 0.11 omega? That is
0.11 omega.
And the 0.11 is the radius, and omega is just they're just using the letter for that. They just wanted us to make sure that we knew the relationship between omega and velocity in this situation.
Okay.
So, and the reason for the negative sign is also able to see within the acceleration, which is that as the velocity slows down, the velocity number is going to get smaller, omega is going to get bigger. And so they're moving in opposite directions, which is also another way of explaining why it's negative 0.11 omega.
Okay, but so when we try to solve question D, then we don't know any specific number when the omega 0 reach to. We only know omega final f. Omega, this is, let's say, is omega.
That's the initial omega. The initial omega, it's not rotating at all, and we are able to figure out when the ball is actually starting to rotate, because that point when v is actually equal to r omega. Before that point, you're getting some rotating, but it's still doing some sliding as well. The point at which it stops sliding and it rolls smoothly is when v equals r omega. That's the definition of v equals r omega, is that the ball is sliding, the ball is rolling smoothly. So if that's not happening, if v doesn't equal r omega, then it's not rolling smoothly. And so what we want to do is, knowing what our initial velocity is with the initial linear acceleration, and knowing what our initial omega is with the initial angular acceleration, we can set those two equal to each other to find out the point in time when v is equal to r omega.
Yeah, I understand the process. Like in the end, we need to find the velocity that equals to r omega. So that's when the ball starts rolling, right?
Right. Yes.
And we don't know. How do we know the numbers? Like how do we know how much v has decreased and how much omega has increased?
Because we know what their accelerations are. We've calculated what both accelerations were.
Yeah, we have all these accelerations, right? But we're asking for how long, so they're asking for time.
Right. So we put them into velocity equations, velocity with respect to time equations using
you just
linear and angular acceleration. So, for example, the velocity equation is negative at plus 8.5. Because
at
plus 8.5, because its initial v naught is 8.5.
Yeah.
So that is our velocity equation, and it's got t in there. And then our omega equation is just alpha t, because there is no initial omega.
Okay, I see. So you make an equation for velocity, this one, linear velocity.
Yes.
And then you make the one for omega. And you both have t. And then you make them equal together with r.
Yes.
Okay, so 3 equations to sum of this.
Yes.
Okay.
And then how far, that's easy enough to do once we know what the time is, because we just plug that into our position function that we can get from our velocity function. And then the linear speed of the ball when smooth rolling begins is just, we know what the time is. We just plug that into our velocity equation, and that tells us what the linear speed is at that point. So once we get those two setting to each other and understanding that v equals r omega only when there's smooth rolling, then everything else makes sense. Mm-hmm. So this, I think, is as hard as he's going to probably do with these kinds of angular acceleration and rotation and stuff like that. But I wanted to make sure that I understood it better, and I do understand it better. So thank you for that.
Thank you, everyone. Any other questions we can work on? Yeah, I just like, what?
I was just going to say, Windsor, if you're wanting, at this point, we can jump back into chapter 12. I just really wanted to get this assistance, and I appreciated the time for it. So.
Question 12.
You can try like question 22.
22. Okay, this one. Um, so the guy, if he wants to remain stable, so the torque has to be, so, okay, so did you finish reading?
I'm still writing things down here.
This is 0.2, 0.4. And the guy is holding this and pushing this part to remain stable.
I'm not sure I understand what it means by the pull by the hands and push by the feet. Oh, I see. So he's trying to.
So this is a feature, a slide. So the guy, he's holding this. You know, when we try to clamp something, so we try to hold, and then we kind of push.
Yeah, I'm seeing it now. I understand. So forces that are happening are gravity is pulling him down. So his body is mg pulling him down. And then there's a normal force from his legs or from the wall pushing against his legs.
Right. So his hand is pulling. There's a pulling force, and there is a pushing force from his feet. I mean, to his feet.
Yeah.
And we know if we want to make him stable, either the force, the net force would be zero, or the torque would be zero, right?
Right.
So now since the so you can see, so now it's not, so from my understanding, you cannot put the force to the net force to be zero. Because
Wait, you can't set the net force to be zero?
wait, you have a friction, right? Yeah, it's friction. Oh yeah, it's just like a, so we'll have to calculate the friction. Wait.
Yeah, there's some frictional forces. The friction forces for his feet,
8.4.
friction is trying to push his feet up, right?
So he's.
I could be wrong on that, but I think that the
friction is pointing up.
Yeah, for his feet.
Yeah, for his feet.
And the same thing for his hands, I guess, is the friction is also pointing up.
Pointing up, yes.
So yeah, go ahead.
So so if we wanna make him stable, we have to find all the forces he's facing. Like one is, see, his downward is the mg.
Yeah. So the forces that are keeping him, if I drew this correctly, and I might not have drawn all of the correct forces, But if I drew all the forces correctly, the forces that are keeping him currently up are the forces of friction.
Yeah, the static friction.
That's, yeah, the static friction force. Those are the only two things. So you set mg equal to the force of the two static frictions plus each other. So force 1 plus the force of static friction 2. And then that should equal mg.
Yeah, so there's two, I mean, on the on the vertical direction, those forces are cancelled out to make him stable.
Yeah.
So if we want to find the pull, so we know, so what caused this friction is the support. Let's say it's pulling this way, so the let's say it's wall is giving him F, a support N, right?
Right.
And then he's kicking this way, so the wall on this side is pulling this way.
So the pull of his hands has to equal that normal force.
Yeah, normal force.
Normal force 1 and normal force 2. So the pull of his hands, so force of hands is equal to the force of the normal force 1, and the force of the feet is equal to normal force 2. And those two equal each other because they're going in opposite directions, right?
Yes.
So the force of his hands and feet have to equal each other?
N1 equal to N2, yeah. And the F1 and F2, they are different because they have different
coefficients of friction. Yeah. Also because those two are being added together to equal mg. So they're not being set equal to each other at all. But that still doesn't help us though, because right now I have an equation for the force of his hands pulling against the wall equaling a normal force that I don't have any way of figuring out. And I have his feet pushing against a wall that is equal to another normal force that I don't know have any way of figuring out.
So this normal force is what we are looking for. What is
right.
the pull?
That exactly. And so we need to figure out,
from mg we can figure out the F, right? Let's just list the equations. Mg equal to F1 plus F2.
Yeah, for the two frictional forces.
Yeah, F1 equal to mu times N.
Yes.
mu1 times N. And the F2 equal to mu2 times N.
Yes.
You're looking for N. Right?
No, because that's, I guess you're right that is the case, isn't it? Because it's the normal force, and that's the normal force. Oh, yeah, I guess you're right. That is exactly what we want to know. Oh, this is a lot easier than I thought it would be.
Yeah, this you just put this 2 with N into this equation and you can solve N because you have
right. So you have wait, hold on a second though. Wait a second. If you have mg is equal to mu1 times normal 1 plus mu2 times normal 2, we still need another equation for our, we also know that n1 is equal to n2, so you can just pop out n1 and put in, or n2 and put in n1, and so then that way we now have mg over mu1 plus mu2 is equal to the normal force.
Right.
And if that that would be the correct answer for that?
Yeah. That should
okay. So then find the horizontal pull of what must be the vertical distance h between hands and feet. The horizontal pole of the vertical distance?
So let me erase this. So they're asking what is the vertical edge, right? Maybe the horizontal.
No, it's asking what must be for the horizontal pole of A. Oh, for the horizontal pole of what we figured out for that normal force. What must be the vertical distance h between hands and feet? And so
I guess we have used torque to calculate, because so we want the torque be 0, and so we know we have the F and the friction, and we have support. Remember, I
Yeah.
drew all the forces applied on the guy, right?
right.
So this support, what is it? So the support to the feet and the hand, this distance you have to, okay, so the supporting the normal force times h plus, so the friction times omega, and then the mg times this distance is the total torque. It's a sum torque, right?
Oh, I guess it depends on what we're making is the moment of torque, or the moment of whatever it's called. The
Let's just find the
moment's about the point.
let's see here. Can you see here?
Okay. I mean,
And
sure. Yeah, that's fine. I
Okay.
was wondering, I was thinking though, wouldn't it make more sense to make it at the feet? Because then that would get rid of that normal force, and it's one less force we have to figure out.
Okay, yeah, it's better. So we have this one. Let's say this is the center. We want so the guy is rotating, right?
Right.
I mean,
well, he's not rotating. That's the point.
tendency.
He should be, but he's not.
Yeah. So we have this tendency. So we want to keep him stable. Then we have to make sure all the torque equal to 0.
Right.
And we just find all the forces and their arms. You know what I mean?
Yeah, that's the issue though with figuring out the radius in this case between that point at his feet and the point at his hands, because we know what the width is, but and I guess we would be able to figure out some angle maybe.
No, it's all vertical and horizontal. So angle it's.
No, there is a difference though in terms of if you see the point where you did his feet.
Yeah.
It's not at the same point straight up for his hands. His hands are over a bit, so there's an angle for that that line. It's not directly above.
Yes, I mean, yeah, this way, but we have to analyze the forces. The forces is horizontal or, how to draw? Is horizontal or vertical. So what I mean is like this force is N. You don't like putting this is N or this is N.
Oh, I see. Because it's just a horizontal. I thought it was okay, and I guess you're right with that point. It doesn't really matter because that point is just a point. It's not anything other than okay.
Yeah.
So if it's a force that is pushing, it is
So we
that
just all the 3 forces. One is the gravity, another is the friction, and then the supporting force.
But the supporting force we're ignoring because of where we set the moment of that point being. So we're ignoring the feet. We're just looking at mg times the distance from there, and then the that force that it is. So the wall is trying to push him in an opposite rotating direction from the way that his feet are trying to push him.
So this is
or that his body is trying to push him. His body is trying to rotate him counterclockwise, and the wall where his hands are is trying to rotate him clockwise, correct?
The hand are rotating.
The wall is trying to push his hands to rotate clockwise.
Oh, let's just focus on the force. I think that's more easy to understand, because when we say the force, we say force pointing down is positive, then pointing up, all the force is pointing up, it will be negative, right?
Sure. But if we're just looking at ones that are going up and down, then the hands aren't part of that, and that's not dealing with torque. Torque would be going in a circle. So up and down would only
right hand rule to define the direction of torque. You know what I mean? You use right hand, you pointing from the radius to the force, and then where your thumb pointing to is the direction of your torque, right?
So you point to, and then so the direction. I'm not familiar with this right hand rule. Can you explain that again?
So let's say so let's say this is like a circular, and then you want to define the torque. This is F.
Okay.
And you use your right hand from the radius to the force, pointing from the radius to the force direction. Then you will have a thumb. You will, and then the thumb is pointing to the direction of torque.
Sure, but what if you had it pointing to the other direction, but at that top? If you have your hand, that's what I'm not understanding, is like how your hand is pointing such that.
If this one, then okay, this is F1, this is F2.
Yeah.
Like this one is your thumb is pointing like up to you, and if you are pointing this one, you see you have to use your like the 4 fingers from this radius and then cross F. The direction of F can indicates the direction you cross your 4 fingers, and then you have a thumb up, but it's pointing to the screen. Let me share my
yeah.
So you have okay for F1. So your point, the 4 fingers are your indicate the radius, and then F1 is pointing this way, right? And you cross. Then your thumb is pointing me. This is the torque, the direction of torque. But if you are look at the F2, so it's also this is also your finger, but you have to cross that way, which is like you cross this way, and then your thumb is pointing to the screen. So this is the torque.
Oh, I see. Okay, I think I understand what you're saying now.
Yeah.
So that depending on where that goes depends on okay.
So in this case, we okay. So for mg, then this is apparently this is the radius, right? This radius is equal to, actually it's equal to d plus omega. It's just like imagine this point, yeah.
But it's not. If you put it at a center of mass, it wouldn't be at the same horizontal point. Is that okay that it's not the same horizontal point for the purposes of that radius?
Yeah, in this case, if we are looking at the mass, the gravity, you can like imagine here's a point. So
and what I'm saying is that's not at the same horizontal point as that red dot. So wouldn't that mean that we would want a line that goes directly to it and not one that just goes horizontally to the left?
Good question, but I don't think so. The
okay.
Reason is, if we will assume his so maybe we can see him as a system, like him and the walls are in a system. So we just try to calculate all the torques together, and we instead of focusing on one point. I think maybe I made a mistake when we are focusing on one point and say the forces.
But I thought that was the whole point for torque, is that you have to say that everything is happening about a particular point. Otherwise, you're not really, like, you're not able to find a radius unless that it's a radius from a particular point.
Let's see other information.
I mean, I could be wrong. I'm not saying I know what's going on here. I'm just saying that, like,
yeah, but we can just for now take the radius as d plus r omega.
okay.
Let me see. But if we try to calculate this, it's not. I just don't know like how that works.
Right. Well, that was my point, was that, like, there would be some kind of angle involved, and I was wondering if there would be some way of, because we know, I was thinking there had to be some way of being able to figure out the angle, because the thing is that we don't even need to know about the main part of the body so much as we wanted to know what the angle would be between the feet and the hands, so then that way we'd be able to know what that height has to be. But
I guess since they are asking you for like horizontal or vertical, we just like take it as, unless it specifically say size the angles, so we can calculate that. But yeah, for
Windsor, are you still with us?
Yeah, I've been trying to figure out, this is a tough problem.
Okay. I just, like, yeah. He gives us something like this. This is one of those situations where I'm like, you know what? I'm just going home.
Yeah, no, for real. I mean, the hardest thing for me is when I like I said, I always just try and Google them and see if they some have a solution. And one of the
Right.
things it was saying, it was acting like, which didn't really make sense to me, that the normal force on his hands from the rock, so not on his feet, on his hands, is also going to the left. And to be honest, I've been stuck. I'm like, why? It seems like in all.
Oh yeah, that absolutely shouldn't be going.
Right? That's what I was saying too.
Yeah, from the rock, it's pushing out, because otherwise his hands would just push through the rock. His hands would literally
Yeah,
just pull everything
exactly. Because the normal force would be going with him. Yeah, it's weird. This is a really tough one.
in. Okay. So go ahead, Judy. You were trying to do the sum of torques, and we can see what we come up with and go from there.
so this is the torque from the gravity, and you plus the torque from the friction. We can try to say the friction. Then if we what's the radius of friction?
The radius of friction? You mean the
Not radius friction, the
coefficient of friction for the feet?
So when we calculate torque, we have to find the F times R, right?
Right. And
So
that's the
the
radius is the question.
The radius, how we find the radius of to calculate torque of friction.
Yeah, that is the $10,000 question right there.
Okay, I did find the answer. You guys can look up. I sent to the chat. It says the radius should be omega.
The radius should be omega, or it should be W.
W.
Hold on, I'm pulling up what you just sent. I'm gonna put it over here so I can look at it separately. And yeah, this is the problem. Force 1 plus force 2 is minus mg. We got that one. And then mg d plus w minus force 1 minus force n1 is force 1 w. Yeah, mgd plus w, which hold on, pulling this up. Okay, so so it's saying that the torque of the first frictional force and the torque of the normal force are going in the same direction. And so F1 we're saying is which one?
No, you just,
between the hands. So the hands are going the same way as...
I mean, you're looking at the explanation for
the torque. I'm looking at the explanation for the torques. I'm not getting that one because it's saying here that it's...
Oh, I see.
It's picking the top point away from the hands as the moment to be calculated. And so that's why the normal force for the feet is N1H, because that's the force and that's the radius H. And that also gives us F1, the friction force, because that's just W away horizontally. But I'm still not sure the D plus W. I guess we're assuming then, yeah, that's the point, I think. And then we're just assuming that the center of mass of the person is at the same level. So it's D plus W.
This is the, okay, D plus W, which is F1 plus W, right?
Yeah, that's the F1 plus W. And it's saying that that one's going clockwise because that makes sense. It's pushing that way. And then the Fn1 down at the bottom where his feet are is also makes sense because that's pushing away, still doing the same clockwise motion. And then the mass pushing down is the only thing that is pushing in a counterclockwise way. Yeah, I think that makes sense.
So we're
also, I love how this says intuitively. Nothing is about this problem is intuitive.
No, it's not.
That's just mean. But yeah, it's I'm just not sure that like is an alive back yeah. The climber encounters a wet rock so that mu1 and mu2 are reduced. What happens to C? To the answer to A and the answer to B.
After the friction getting smaller, yes.
Then he has to hold on tighter because it'll it won't be supporting him as much. The friction. I mean, like, I'm only answering that intuitively, just as it makes sense that.
So for question B, we still have to figure out. So you're saying this is the one point they're doing.
That's the moment that they're using. So then that way you can get to the hands and you can get to the feet with just straight lines.
Yes. Yes.
And then they're saying that the body is just going to be horizontal as well. So we're getting W plus D, which I'm not sure I agree with, but we'll go ahead and acknowledge that that's what they've decided. Because that's finding the center of mass of a person becomes more complicated. So I think that's why they're just like, we're just going to do this simply, you know. But yeah, and so then once you are able to get all of that, finding H is actually a lot easier from all of that because it's just getting H by itself. It's just understanding the way to put the torques appropriately. I am so worried about this exam tomorrow. I'm not going to lie. This is just...
But I don't think they will ask a question like that.
I hope not. I really hope not. I mean, it as long as I can just kind of see like where these forces are applying their weight, like, and then it should be okay, and it should be pretty straightforward, because then it's just like set everything equally to each other. Do a free body diagram. We've got all these forces going in all these directions, and then, you know, that should make sense. It's just making sure that I'm able. Although the way that he was doing it was like with you know, hanging masses on some kind of horizontal bar. So I feel like that's more likely than this kind of like person situation. So
Yeah, no, I think you're right. I think it's going to be a hanging mass one, or I could see one like I guess it's for problem 26, that guy with the leaning against the wall. You know what I mean? Like the ladder type problem.
Oh yeah, if there isn't a ladder problem on this, I will be shocked. I'm sure that there's going to be a ladder problem.
Me too.
Like that one, I actually feel pretty okay about. I've done enough of that to understand about what's going on. Although, Windsor, did you do problem number? Hold on, I need to look it up here. Got to jump back here. Okay. So this was, I need to go to chapter 12. And then, where is it? Yeah, did you do number 7, that ladder problem?
Give me 1 second. Let me look at the thing.
The one right above the Brady Bunch. Weird question. Anyway.
No, I didn't do number 7.
Okay, because I was able to get the magnitude of the force on the window from the ladder pretty easily. Like, I understand how all of that works now. But the magnitude of the force on the ladder from the ground and the angle of that force on the ladder just left me so terribly confused. And I wasn't able to find anything that was because every example that I looked at that was similar to this one didn't do anything like that. Like everything was just real straightforward and simple. So I assume that I probably won't need to know how to do those things because of like how nobody else is talking about it. But it was just, I was going to see if anybody else had figured it out. But we're out of time, so it's not a big deal. And I'll do some more studying tonight. But thanks, Judy, for
yeah, thank you.
talking
Thank
this
you
through
for
with us.
working through it with us.
Yeah, I really enjoy we can work on some questions together. It's very interesting. Hope we can like make some concept clarified.
Well, I at the very least, I feel better about the rolling ball. Like, I don't know about anything else, but I at least feel clear about that.
Just to
Yeah.
learn. Yeah. Thanks,
So.
Winter. Thanks, Alex.
That's
No,
my
thank
pleasure.
you. Appreciate it. Yeah.
So
Okay, then I'll see you next week then.
yeah, sounds good. Bye, everyone.
Good luck.
Take
Bye.
care, everybody.